Hey guys, tonight we're traveling back to the highlands of ancient Ethiopia, where civilizations looked upward long before the invention of the telescope, long before European astronomers claimed dominance over celestial knowledge. We're going to explore how Ethiopian astronomers, priests, and scholars developed sophisticated methods for tracking the movements of stars, planets, and the sun itself. Methods that would guide agricultural cycles, religious observances, and the very structure of time for thousands of years. This is a story about patience, observation, and the quiet determination of people who understood that the heavens held secrets worth decoding, one slow night at a time. The Ethiopian highlands have always been a place where earth meets sky in a particularly intimate way. At elevations ranging from 6,000 to 10,000 feet above sea level, the air is thin and remarkably clear. On cloudless nights, and there are many such nights during the dry season, the stars appear with a brilliance and clarity that lowland observers can barely imagine. The Milky Way stretches across the darkness like a river of light. Individual stars seem close enough to touch, and the planets move with a stately precision that begs to be measured and understood. For the people who lived in these highlands, particularly in the regions around Aksum, and later in the spiritual centers of Lalibela and Gondar, the night sky was not merely beautiful, it was a text to be read, a calendar to be consulted, and a map to be studied. The roots of Ethiopian astronomy stretch back to the kingdom of Aksum, which flourished from approximately the 1st to the 7th centuries CE, though its origins lie even deeper in the pre-Aksumite Deemed kingdom of the 10th to 5th centuries BCE. Aksum was a major trading power, its merchants traveling to Egypt, Arabia, Persia, and India, bringing back not only goods, but also ideas, mathematical concepts, and astronomical knowledge. The Aksumites were in contact with Hellenistic learning centers, with Roman astronomical traditions, with Arabian sky watchers, and with Indian mathematical innovations. Yet rather than simply adopting these foreign systems wholesale, Ethiopian scholars developed their own distinctive approaches, blending imported knowledge with indigenous observation traditions that had been developing for centuries. The earliest evidence of systematic astronomical observation in Ethiopia comes from architectural alignments and the careful orientation of important structures. The great stelae of Aksum, those towering obelisks carved from single pieces of granite, some reaching heights of over 70 feet, were not erected at random angles. Archaeological surveys conducted in the late 20th and early 21st centuries revealed that many of these monuments align with celestial events, particularly with the rising and setting points of the sun at the solstices and equinoxes. The largest standing stela, known as the Obelisk of Aksum, appears to have been positioned with careful attention to solar angles, creating specific shadow patterns at significant times of the year. But why did this matter? For an agricultural society dependent on the rhythms of the rainy seasons, understanding the solar year was not an academic exercise. It was a matter of survival. The Ethiopian highlands experience two primary rainy seasons, the Belg, or small rains, from February to May, and the Kiremt, or main rains, from June to September. Between these seasons lie periods of dryness, when planting, tending, and harvesting must occur with precise timing. Miss the optimal planting window by even a week, and an entire year's crop might fail. Plant too early, and seeds rot in dry soil. Plant too late, and crops don't mature before the rains end. The sun's annual journey across the sky provided the most reliable indicator of when these seasonal transitions would occur. By observing the point on the horizon where the sun rose each morning, Ethiopian astronomers could track its slow movement from south to north and back again over the course of a year. At the winter solstice, around December 21st in the modern calendar, the sun reaches its southernmost rising point. Each day thereafter, it rises slightly further north along the eastern horizon until it reaches its northernmost point at the summer solstice around June 21st. Then begins its return journey south. The equinoxes, when day and night are of equal length, mark the midpoints of this celestial migration, occurring in late March and late September. For Ethiopian observers without telescopes or precision instruments, tracking these solar movements required careful attention to landscape features and the construction of observational aids. Horizon markers became crucial tools. A distinctive mountain peak, a gap between hills, a particular rock formation. These natural features served as reference points against which to measure the sun's position. Observers would note precisely where the sun rose relative to these markers on important dates, gradually building up a mental or recorded map of the sun's annual path. Some communities erected artificial markers, stone pillars, wooden posts, or constructed sighting lines to make these observations more precise. The process was slow and required patience, but modern people, accustomed to instant digital readings, can barely comprehend. An astronomical observer in ancient Aksum might spend years, even decades, refining measurements and noting patterns. The work demanded dedication across generations, with knowledge being passed from master to student, from priest to initiate, from elder to younger observer. Each generation would add slight refinements to the accumulated wisdom, correcting errors, noting anomalies, and gradually building a more complete understanding of celestial patterns. Religious institutions played a central role in this astronomical work. The Ethiopian Orthodox Tewahedo Church, which traces its roots to the conversion of the Aksumite king Ezana in the 4th century CE, became the primary custodian of astronomical knowledge. Monasteries and churches served as observatories, libraries, and training centers for astronomical study. The connection between religion and astronomy was not incidental, it was fundamental. The church required accurate calendar keeping to determine the dates of religious festivals, particularly the calculation of Easter, which depends on both solar and lunar cycles. The timing of fasting periods, feast days, and liturgical seasons all demanded precise knowledge of celestial movements. The Ethiopic language, Ge'ez, developed specialized vocabulary for astronomical concepts, suggesting a long tradition of sophisticated sky watching. Terms existed for different types of celestial bodies, for various phases of the moon, for planetary positions, and for the divisions of the sky. Ancient manuscripts written in Ge'ez contain astronomical tables, calculation methods, and observational records that demonstrate the depth of Ethiopian astronomical knowledge. These texts were laboriously copied by scribes in monastery scriptoria, preserved through centuries of political turmoil, warfare, and environmental challenges. One particularly important class of astronomical texts in the Ethiopian tradition is the genre known as Bahir Hasab, or Ocean of Calculation. These are essentially astronomical and calendrical computation manuals, containing the mathematical methods necessary to calculate the date of Easter according to the complex rules established by early Christian councils. The Bahir Hasab texts represent a remarkable fusion of mathematical astronomy, theological requirements, and practical observation. They include tables of lunar and solar cycles, methods for calculating epochs, the age of the moon on January 1st, instructions for determining the golden number and the Sunday letter, and algorithms for reconciling the lunar calendar used for Easter with the solar calendar used for fixed feast days. The mathematical sophistication required for these calculations should not be underestimated. The Bahir Hassab computations involve working with large numbers, understanding cyclical patterns that span 19 years, the Metonic cycle relating lunar and solar years, and performing complex arithmetic operations without modern calculating tools. Ethiopian church scholars developed various mnemonic devices, finger counting methods, and calculation shortcuts to manage these computations. Some monasteries possessed counting boards or computational aids, physical tools to help track the various cycles and perform the necessary arithmetic. But the Ethiopian astronomical tradition extended beyond purely religious calendar keeping. There is evidence that astronomical knowledge informed navigation, timekeeping, and even medical practice. Travelers crossing the vast stretches of Ethiopian territory, whether merchants moving goods between highland and lowland regions or pilgrims journeying to distant monasteries, use stellar navigation to find their way. The North Star, Polaris, provided a fixed reference point for determining direction at night. The rising and setting positions of prominent stars and constellations helped travelers orient themselves and estimate the time of night. The division of the night into watches for prayer, a practice adopted from early Christian traditions, required a practical method for telling time without mechanical clocks. Ethiopian monks developed systems based on stellar positions, learning to recognize which stars would be visible at which positions in the sky during different hours of the night and at different seasons of the year. A monk responsible for waking the community for midnight prayers needed to observe the stars and recognize when the appropriate hour had arrived. This was not a simple matter of noting when one specific star appeared. It required understanding how the entire visible sky rotated throughout the night and how that rotation shifted gradually across the seasons as the Earth moved in its orbit around the Sun. Ethiopian medical texts also show astronomical influences, reflecting the widespread ancient belief that celestial bodies influenced health and illness. While modern medicine has abandoned such notions, for ancient practitioners, tracking planetary positions and lunar phases seemed to correlate with various health patterns. Whether these correlations were genuine or coincidental, the belief drove detailed observation and record-keeping that contributed to the overall body of astronomical knowledge. The tools available to Ethiopian astronomers were simple by modern standards, but adequate for their purposes. The human eye, properly trained, is capable of remarkably precise observations. An experienced observer can detect the position of a star or planet to within about 1 degree, roughly twice the width of the full moon. This level of precision, accumulated over many observations and combined with careful record-keeping, allows for the detection of planetary movements, the precession of the equinoxes, and various other celestial phenomena. Sighting instruments made from wood, stone, or bone could improve observational precision. A straight staff, planted vertically in level ground, becomes a simple sundial, its shadow marking the sun's movement across the sky. By marking the shadow's position at sunrise, noon, and sunset on different days, an observer can track the changing length of days across the year and determine the dates of solstices and equinoxes. More sophisticated instruments might include sighting tubes to narrow the field of view, cross sticks to create angular measurements, or water levels to establish precise horizontal references. The measurement of angles was particularly important. The angular distance between stars, measured in degrees as we would describe it today, though Ethiopian astronomers used different units, could be estimated using body parts. A hand held at arm's length spans about 10 degrees of sky. A fist covers roughly 10 degrees, while a finger width represents about 1 degree. A stretched hand from thumb to little finger spans about 20 degrees. Using these natural measuring tools, an observer could describe stellar positions and movements without any manufactured instruments whatsoever. But precision measurements and mathematical calculations alone don't capture the full scope of the Ethiopian astronomical tradition. There was also a rich tradition of stellar lore, constellation recognition, and the incorporation of celestial observations into cultural narratives and seasonal wisdom. Ethiopian farmers, even those without formal astronomical training, developed practical sky knowledge that guided their work. They knew which stars appeared when planting time approached, which constellations marked the coming of the rains, and which celestial signs warned of drought or favorable conditions. The question that Ethiopian astronomers grappled with, generation after generation, was fundamentally this: how do we create a stable system of timekeeping that honors both the sun's annual cycle and the moon's monthly phases, while serving the practical needs of agriculture and the liturgical requirements of our faith? The answer they developed, the Ethiopian calendar system, would prove to be one of their most enduring contributions, and it raises fascinating questions about how different cultures conceptualize time itself. But to understand that calendar system fully, we must first explore how these early astronomers refined their observations and developed the mathematical tools that made precise calendar calculation possible. How did they bridge the gap between raw observation and systematic prediction? What methods allowed them to forecast celestial events years in advance? The transition from simple observation to predictive astronomy required Ethiopian scholars to develop systematic methods for recording data, recognizing patterns, and translating those patterns into mathematical relationships. This was not work that could be accomplished in a single lifetime, nor was it the product of isolated genius. Rather, it emerged from the accumulated efforts of countless observers working across centuries, each contributing small refinements to a growing body of knowledge that would eventually allow them to predict celestial events with remarkable accuracy. The fundamental challenge facing any pre-telescopic astronomer is the limitation of human perception. We stand on a rotating sphere, orbiting a star, surrounded by other planets also in motion, all while the entire solar system slowly drifts through a galaxy that itself is moving through space. Yet from our earthly vantage point, we perceive none of this motion directly. Instead, we see an apparent dome of sky above us, with celestial objects appearing to move in regular but complex patterns. Unraveling the true geometry of these motions from their apparent movements requires careful observation, patient record-keeping, and mathematical insight. Ethiopian astronomers began with the most obvious celestial cycle, the daily rotation of the sky. Each night, stars rise in the east, arc across the southern sky for observers in the northern hemisphere, and set in the west. This apparent rotation is caused by Earth's actual rotation, though ancient astronomers naturally believed the sky itself was rotating around a stationary Earth. The practical effect was the same. The entire celestial sphere appeared to complete one full rotation approximately every 24 hours. But this approximately concealed an important subtlety. The actual period of Earth's rotation, one sidereal day, is about 23 hours and 56 minutes, not exactly 24 hours. The difference arises because as Earth rotates, it also moves along its orbit around the Sun. Each day, Earth travels roughly 1 degree around its orbit, meaning it must rotate slightly more than 360 degrees for the Sun to return to the same position in the sky. This extra rotation accounts for the 4-minute difference between a sidereal day, measured by the stars, and a solar day, measured by the sun. Ethiopian astronomers discovered this distinction through careful observation. They noticed that stars rose about 4 minutes earlier each night, relative to sunset. A star that rose exactly at sunset one evening would rise 4 minutes before sunset the next evening, 8 minutes before the following evening, and so on. Over the course of a month, this accumulated to about 2 hours of difference. Over a year, the difference completed a full cycle, with each star returning to rise at sunset after approximately 365 days. This observation led to a crucial insight. There are really 2 different ways to measure a year. The tropical year, the time between successive spring equinoxes, is approximately 365.2422 days. This is the year that matters for seasons and agriculture. But there's also the sidereal year, the time it takes for the sun to return to the same position relative to the distant stars, which is approximately 365.2564 days. The difference between these 2 year lengths, about 20 minutes, is caused by the precession of the equinoxes, a slow wobble in Earth's axis that takes about 26,000 years to complete one full cycle. While Ethiopian astronomers may not have understood precession in modern terms, careful observers certainly noticed its effects over long periods. Ancient stellar positions recorded in manuscripts gradually became inaccurate over centuries, requiring periodic updates to maintain their utility. This must have puzzled early astronomers. Why would the stars themselves seem to shift their positions relative to the seasonal markers? The answer, that Earth's axis slowly wobbles like a spinning top, would not be fully understood until much later, but the observational reality had to be confronted and accommodated. The moon presented its own set of challenges and fascinations. Unlike the sun and stars, which move with relatively simple and regular patterns, the moon's motion is complex and irregular. The moon orbits Earth approximately every 29.5 days, passing through its familiar cycle of phases from new moon to full moon and back again. This lunar month, technically called a synodic month, is the basis for lunar calendars used by many cultures, including the Islamic calendar and the traditional Jewish calendar. But the moon's orbit is not perfectly circular, and it's tilted relative to Earth's orbit around the sun. This means the moon's apparent speed varies throughout its monthly journey, sometimes moving more quickly across the sky, sometimes more slowly. The time between successive new moons varies by several hours, ranging from about 29 days and 6 hours to 29 days and 20 hours, with an average of about 29 days, 12 hours, and 44 minutes. For Ethiopian astronomers attempting to create a calendar that honored both solar and lunar cycles, this irregularity posed significant problems. A year of 12 lunar months totals only about 354 days, roughly 11 days shorter than a solar year. If you began a purely lunar calendar with the new year at the spring equinox, after just 3 years, the calendar would have drifted more than a month away from its starting point. Within 15 years or so, the calendar would be completely out of sync with the seasons, summer months occurring in winter, planting times arriving at harvest season. The ancient Hebrews, Babylonians, and Greeks had all grappled with this solar-lunar discrepancy and developed various solutions involving intercalation, the periodic insertion of extra months to bring the lunar calendar back into alignment with the solar year. The Ethiopian Church, which needed to calculate Easter according to rules that involved both solar and lunar elements, inherited calculation methods from these earlier traditions, particularly from the Alexandrian Church, which had been a major center of astronomical learning in the early Christian world. The rule for calculating Easter, established by the Council of Nicaea in 325 CE, states that Easter should fall on the first Sunday following the first full moon after the spring equinox. This seemingly simple rule actually requires sophisticated astronomical calculation. You must know the date of the spring equinox, a solar calculation, determine when the first full moon after that date occurs, a lunar calculation, then find the following Sunday, a calendrical calculation involving the 7-day week cycle. These 3 cycles, the solar year, the lunar month, and the 7-day week, do not align neatly, making Easter a movable feast that can occur on any Sunday between late March and late April. Ethiopian church scholars mastered a calculation system based on the Metonic cycle, named after the Greek astronomer Meton, who described it in the 5th century BCE, though the cycle was certainly known to earlier Babylonian astronomers. The Metonic cycle represents a remarkable mathematical relationship. 19 solar years equal almost exactly 235 lunar months. More precisely, 19 years of 365.2422 days, each totals 6,939.6018 days, while 235 lunar months of 29.53059 days each totals 6,939.6885 days, a difference of less than 3 hours out of nearly 7,000 days. This near-perfect coincidence meant that lunar phases repeat on the same dates in a 19-year cycle. If a full moon occurred on June 15th in one year, you could be confident that 19 years later, a full moon would again fall on or very near June 15th. This allowed the creation of perpetual lunar calendars that could predict moon phases for any date by knowing where in the 19-year cycle you were. The position within this cycle was called the golden number, and it became a fundamental element of ecclesiastical calendar calculation. Ethiopian computists, specialists in calendar calculation, memorized extensive tables showing the relationship between golden numbers, solar years, lunar months, and the dates of Easter. These tables, preserved in Bahir Hassab manuscripts, represent the accumulated computational wisdom of generations. A skilled computist could determine the date of Easter for any year, past or future, by working through a series of calculations involving the golden number, the solar cycle, a 28-year pattern relating calendar dates to days of the week, and various correction factors. But these calculations were not merely abstract mathematical exercises. They had to produce results that matched observable reality. Ethiopian astronomers regularly checked their computational predictions against actual observations. When was the new moon actually first visible? When did the full moon rise? Did these observed events match the dates predicted by the calculation tables? When discrepancies appeared, they had to be analyzed, understood, and either accommodated through calculation adjustments or explained as observational errors. The observation of the first visible crescent moon after the new moon was particularly important and particularly challenging. The new moon itself, when the moon passes between Earth and the Sun, is invisible, lost in the sun's glare. But a day or two after new moon, the thin crescent first becomes visible in the western sky just after sunset. This moment of first visibility depends not only on the moon's position, but also on atmospheric conditions, the observer's elevation and location, the moon's angle relative to the horizon, and the observer's visual acuity, Ethiopian observers developed practical wisdom about moon sighting. They knew that first visibility was most likely when the moon set at least 40 minutes after the sun, when the moon was at least 7 degrees above the horizon at sunset, and when the moon's angular separation from the sun exceeded about 10 degrees. These practical rules emerged from countless observations, gradually refined to predict when moon sighting would be possible at different times of year from different locations in the Ethiopian highlands. The stellar observations required different techniques. While the sun and moon move against the background of stars, the stars themselves maintain fixed patterns relative to each other, at least over the timescale of a human lifetime. These fixed patterns, the constellations, served as a celestial map against which the motions of the sun, moon, and planets could be measured. Ethiopian astronomy inherited constellation concepts from multiple traditions. Some constellation names and patterns came from Greco-Roman sources, transmitted through contact with Alexandria and the broader Mediterranean world. Others derived from Arabian astronomical traditions, which themselves synthesized Indian, Persian, and Hellenistic elements. Still others appear to be indigenous developments based on Ethiopian cultural references and local mythological traditions. The zodiac, that band of 12 constellations through which the sun appears to move during its annual journey, held particular significance. The sun's position in the zodiac provided a convenient way to describe its progress through the year. When the sun entered Aries around the spring equinox, farmers knew planting time approached. When it reached Cancer at the summer solstice, they prepared for the main rains. The sun's passage through Libra at the autumn equinox signaled harvest time, while its position in Capricorn at winter solstice marked the cold season. But unlike the sun and moon, whose motions are relatively straightforward, the planets presented a genuine puzzle. The word planet derives from a Greek term meaning wanderer, and these celestial bodies certainly lived up to that name. 5 planets are visible to the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn. And ancient astronomers noticed them because, unlike stars, they moved against the background of the fixed constellations. The planets' motions were irregular and sometimes baffling. Most of the time, they moved slowly eastward through the zodiac constellations, the same direction the sun and moon traveled. But periodically, each planet would slow down, stop, reverse direction, and move westward for a period. This backward motion is called retrograde motion, then stop again and resume its eastward journey. The duration and frequency of these retrograde periods differed for each planet. We now understand that retrograde motion is an optical illusion caused by the relative motion of Earth and the other planets as they orbit the sun at different speeds. But for ancient observers who believed Earth was stationary, retrograde motion was genuinely mysterious. Various theoretical models were proposed to explain it: epicycles, eccentric circles, and other geometric constructions. But Ethiopian astronomers, like most pre-telescopic astronomers, focused primarily on describing and predicting these motions rather than explaining their underlying causes. The practical challenge was creating tables that could predict where each planet would be at any future date. This required years of careful observation to establish each planet's average motion through the zodiac, the typical duration of its retrograde periods, and the intervals between successive retrogrades. Jupiter, the slowest moving of the visible planets, takes nearly 12 years to complete one circuit through the zodiac, meaning a full observation cycle required more than a decade. Saturn moves even more slowly, requiring about 29 years for one complete circuit. These long observation periods meant that planetary astronomy was necessarily a multi-generational enterprise. A single observer might watch Jupiter complete one full circuit through the zodiac, but understanding the subtle variations in its motion and developing accurate predictive models required comparing observations across multiple circuits, a project spanning several human lifetimes. This is where institutional continuity became crucial. Monasteries and church institutions provided the long-term stability necessary for sustained astronomical programs. Ethiopian manuscripts contain planetary tables showing predicted positions for years and even decades into the future. These tables represent sophisticated computational work, incorporating observations, mathematical modeling, and periodic corrections based on new observations. The accuracy of these predictions varied. Some were quite good, others less so, but the mere existence of such tables demonstrates a commitment to systematic predictive astronomy rather than mere descriptive observation. Beyond the technical aspects of observation and calculation, there was also an aesthetic dimension to Ethiopian astronomy. The night sky was not merely a collection of data points to be measured and tabulated. It was beautiful, awe-inspiring, and sacred. Religious texts drew parallels between the perfect, unchanging motions of the heavens and the divine order that governed all creation. The stars in their courses, moving with mathematical precision through their eternal circuits, reflected the wisdom and power of the Creator. This theological dimension gave astronomical work a spiritual significance beyond its practical utility. To study the heavens was to read the book of nature, to discern the mathematical harmonies embedded in creation, to glimpse the mind of God reflected in the clockwork of the cosmos. The long hours spent in patient observation, the careful recording of data, the laborious calculations, all of this was not merely technical work, but a form of worship, a way of honoring the Creator by coming to understand creation more fully. Yet for all their sophistication, Ethiopian astronomers remained limited by their tools and theoretical frameworks. Without telescopes, they could not see Saturn's rings, Jupiter's moons, or the phases of Venus, observations that would eventually demonstrate that the Earth orbits the Sun, rather than vice versa. Without accurate mechanical clocks, they could not make the precision timing measurements that would later revolutionize astronomy. Without the mathematical language of calculus and analytical geometry, they could not model celestial motions with the accuracy that would later become possible. But perhaps more importantly, they lacked a theoretical framework that encouraged questioning the fundamental assumption that Earth was stationary at the center of creation. The Ptolemaic model of a geocentric cosmos, inherited from Greek astronomy, seemed to explain the observations adequately, or at least no observation accessible to pre-telescopic astronomers definitively contradicted it. The heliocentric model, though proposed by some ancient Greek thinkers and later revived by Copernicus in the 16th century, would not become widely accepted until telescopic observations made the geocentric model untenable. Yet within these limitations, Ethiopian astronomers achieved remarkable things. They created a functional calendar system that served their society's needs for over a millennium. They developed computational methods that allowed accurate prediction of lunar phases and solar positions. They preserved and transmitted astronomical knowledge through periods of political upheaval, warfare, and social transformation. And they established an intellectual tradition that valued careful observation, systematic record-keeping, and mathematical reasoning. The question that naturally arises is, how did all of this technical astronomical work translate into practical calendar keeping? How did observations of stars and calculations of lunar phases become the calendar that organized daily life agricultural work, and religious observance? The answer lies in the unique structure of the Ethiopian calendar itself, a system that represents one of the most distinctive timekeeping traditions still in use anywhere in the world. But understanding that calendar requires understanding not just astronomy and mathematics, but also the cultural and religious context that shaped its development and the practical needs it was designed to serve. How did Ethiopian scholars synthesize all these elements into a coherent system of time? The Ethiopian calendar that emerged from centuries of astronomical observation and mathematical refinement is not a historical curiosity gathering dust in museum archives. It remains the official calendar of Ethiopia today, used by millions of people for civil, agricultural, and religious purposes. This living continuity makes Ethiopia one of the few places on Earth where an ancient calendrical system, rooted in pre-telescopic astronomical traditions, still structures everyday life in the 21st century. Understanding how this calendar works and why it has endured reveals something profound about the relationship between astronomical knowledge and cultural identity. The Ethiopian calendar is a solar calendar, meaning its year is based on the Earth's orbit around the Sun, rather than the Moon's phases. However, it incorporates lunar calculations for determining the date of Easter and other movable religious feasts. The structure of the Ethiopian year reflects the same basic framework as the Julian calendar introduced by Julius Caesar in 45 BCE, 12 months of 30 days each, plus a 13th month of 5 or 6 days to complete the year. This 13-month structure is why the Ethiopian calendar is sometimes called the Coptic calendar, reflecting its close relationship with the calendar used by the Coptic Orthodox Church of Egypt. The 12 regular months bear names that derive from ancient Egyptian month names transmitted through Coptic into Ge'ez, Meskerem, Tikimt, Hidar, Tassas, Tir, Yekatit, Megabit, Miazia, Ginbot, Sine, Hamle, and Nehase. The 13th month, Pagum, contains 5 days in regular years and 6 days in leap years. A leap year occurs every 4 years without exception, making the Ethiopian calendar's average year length 365.25 days, exactly the same as the Julian calendar, but slightly longer than the true tropical year of 365.2422 days. This small discrepancy, about 11 minutes per year, accumulates over centuries. The Julian calendar gains approximately 1 day every 128 years relative to the tropical year. This is why Pope Gregory XIII reformed the Western calendar in 1582, introducing the Gregorian calendar with its more complex leap year rules. Years divisible by 100 are not leap years unless also divisible by 400 by 400. This Gregorian system produces an average year of 365.2425 days, much closer to the true tropical year and accurate to within 1 day every 3,236 years. Ethiopia never adopted the Gregorian reform. The Ethiopian Orthodox Church, like other Oriental Orthodox churches, maintained its traditional calendar system, resulting in a calendrical divergence that persists to this day. The Ethiopian calendar currently runs about 7 to 8 years behind the Gregorian calendar in year numbering, so while the Gregorian year 2025 is underway, Ethiopia is in the year 2017 or 2018, depending on the time of year. This difference arises from different calculations of the year of Christ's birth. Ethiopian computists arrived at a date about 7 years later than the calculation adopted in Western Christianity. But the year number is less significant than the date within the year, because the Ethiopian calendar follows Julian leap year rules, while the Gregorian calendar uses modified rules, and because the Gregorian reform included a one-time adjustment that deleted 10 days, later expanded to 13 days as the calendars continued to diverge. The Ethiopian calendar is currently 13 days behind the Gregorian calendar. Ethiopian New Year, which falls on Mescharim 1 in the Ethiopian calendar, corresponds to September 11th in the Gregorian calendar, or September 12th in Gregorian leap years. This calendrical difference has practical implications in modern Ethiopia. Government offices, schools, and businesses must often work with both calendar systems, the traditional Ethiopian calendar for internal purposes and religious observances, and the Gregorian calendar for international communication and coordination. Documents may bear two dates, newspapers print both calendrical systems, and calendars often show both month designations. This dual calendar reality creates a daily reminder of Ethiopia's distinctive cultural heritage and its connection to ancient astronomical traditions. The religious dimension of the calendar remains central to its significance. The Ethiopian Orthodox Church organizes its liturgical year around a complex cycle of feasts, fasts, and commemorations that depend on accurate calendar calculation. The most important of these is Easter, which, as we've discussed, requires determining the first Sunday after the first full moon following the spring equinox. The Ethiopian Church calculates Easter using the Alexandrian method, which sometimes produces dates different from the Western Easter calculation, adding another layer of calendrical complexity. The calculation of Easter in the Ethiopian tradition involves determining several key values for any given year. First is the golden number, representing the year's position in the 19-year Metonic cycle. This is calculated by a simple formula. Divide the Ethiopian year by 19, and the remainder plus 1 gives the golden number. Next comes the epact, which represents the age of the moon, in days on the first day of the year. The epact advances by 11 days each year, with adjustments when it exceeds 30 to keep it within the range of a lunar month. Ethiopian computists also calculate the Sunday letter, which identifies which day of January first falls on and thus helps determine when Sundays occur throughout the year. The Sunday letter cycles through 7 values in a repeating pattern, but this pattern is disrupted by leap years, which require tracking both a Dominical letter for the period before February 29th and a different one for the period after. The interaction between the golden number, the epact, and the Sunday letter determines the date of Easter for any year. These calculations, which might seem arcane to modern readers accustomed to simply looking up dates on printed or digital calendars, were performed manually by Ethiopian church scholars for centuries. The Bahir Hassab manuscripts provided the necessary tables and algorithms, but actually executing the calculations required mathematical skill, attention to detail, and often several hours of careful work. Errors in Easter calculation were considered serious matters, as they could lead to the entire church observing feasts and fasts on incorrect dates, disrupting the rhythm of religious life. Beyond Easter, the Ethiopian liturgical calendar includes numerous fixed feasts commemorating saints, biblical events, and church traditions. Each month contains multiple feast days, and the calendar of commemorations is so dense that nearly every day of the year has some religious significance. This rich liturgical calendar creates a rhythmic structure to time, marking the passage of weeks and months, not just by number, but by the succession of religious observances, each with its own traditions, prayers, and sometimes dietary requirements. The fasting traditions of the Ethiopian Orthodox Church are particularly demanding and closely tied to the calendar system. Faithful adherents fast, abstaining from all animal products for roughly 250 days per year, including every Wednesday and Friday, commemorating Jesus' betrayal and crucifixion. The entire 55-day Lenten period before Easter, the 40-day Advent fast before Christmas, and various other designated periods. Correctly observing these fasts requires knowing exactly where you are in the liturgical calendar, which in turn depends on the accurate astronomical calculations that determine the calendar's structure. The agricultural calendar, while less formally codified than the religious calendar, was equally important to rural Ethiopian communities. Farmers needed to know when to prepare fields, when to plant different crops, when to expect rains, and when to harvest. The Ethiopian calendar's month names became associated with specific agricultural activities and seasonal expectations. Mescharim, the first month, September to October, in the Gregorian calendar, marks the end of the main rains and the beginning of harvest season for some crops. Tikimpt, October-November, continues the harvest. Hidar, November-December, is a time for threshing and storing grain. The alignment between calendar months and agricultural activities was not perfect. Weather patterns vary by elevation and region across Ethiopia's diverse topography, but it provided a general framework that farmers could adapt to local conditions. The calendar also encoded folk wisdom about weather patterns, with specific days associated with expectations about rain, temperature, or wind. Some of these associations may have had observational bases in long-term weather patterns, while others were more superstitious, but together they created a rich texture of temporal meaning beyond mere date-keeping. The preservation of astronomical knowledge through the centuries depended on institutional continuity and the training of successive generations of scholars. Monasteries served as the primary centers of learning, where young monks received instruction in reading and writing ge'ez, basic mathematics, calendar calculation, and astronomical observation. The training was rigorous and could extend over many years. A student might spend several years simply mastering the ability to read and write ge'ez script before progressing to mathematical studies, and several more years learning the computational methods necessary for calendar calculation. The pedagogical methods emphasized memorization and repetition. Students memorized extensive tables of numbers, learning the golden numbers, epochs, and other key values for all 19 years of the Metonic cycle. They memorized calculation algorithms as verbal formulas, often rendered as poetry or rhythmic prose to aid retention. They practiced performing calculations repeatedly until the methods became automatic. This educational approach produced scholars who could carry vast amounts of calendrical knowledge in memory, able to perform complex calculations without reference materials when necessary. Manuscript production was itself an astronomical act of sorts, requiring careful attention to time. Scribes who copied astronomical tables and calculation manuals had to work with extreme accuracy. A single copied digit error could corrupt an entire table of values. The work was slow and painstaking, performed in monastery scriptoria by candlelight or the dim illumination filtering through small windows. Many manuscripts include colophons, scribal notes at the end, recording the date of copying, the name of the scribe, and sometimes prayers for forgiveness of any errors that might have crept into the text despite careful efforts. These manuscripts, preserved in monastery libraries throughout Ethiopia, represent an invaluable historical record of astronomical knowledge. Some date back many centuries, their vellum pages darkened with age, their ink fading, but still legible. Others are more recent copies, part of the ongoing tradition of manuscript production that continues even in the modern era. Collectively, they document not just the content of Ethiopian astronomical knowledge, but its transmission across time, showing how knowledge was maintained, adapted, and occasionally lost and recovered through periods of upheaval. The 20th century brought profound challenges to these traditional knowledge systems. Italian occupation from 1936 to 1941 disrupted monastery life and led to the destruction of some manuscripts and institutions. The subsequent decades of political instability, including the communist Derg regime from 1974 to 1991, further marginalized traditional religious institutions and the knowledge they preserved. Modernization brought printed calendars, mechanical and digital clocks, and international calendar standards that seemed to render traditional astronomical knowledge obsolete. Yet the knowledge endured. The Ethiopian calendar remained official. The church continued to calculate its feasts and fasts, and scholars continued to study the traditional methods. In recent decades, there has been renewed interest in Ethiopia's astronomical heritage, driven partly by national pride in this distinctive cultural tradition and partly by academic interest in the history of science. Researchers have studied the manuscripts, interviewed elder scholars who still practice traditional calculation methods, and worked to document and preserve this knowledge before the last practitioners pass away. Modern Ethiopian scholars have also worked to reconcile traditional astronomical knowledge with contemporary scientific understanding. They recognize that the geocentric model underlying traditional Ethiopian astronomy is not literally correct. The Earth does orbit the Sun, not vice versa. But they also appreciate that for the practical purposes of calendar keeping and naked-eye observation, the traditional methods work perfectly well. The apparent motions of celestial bodies, as seen from Earth's surface, are accurately described by traditional methods, even if the underlying theoretical model is incorrect. This reconciliation between traditional knowledge and modern science reflects a broader pattern in how cultures around the world are reassessing indigenous and historical knowledge systems. Rather than dismissing pre-modern astronomy as mere superstition or primitive error, contemporary historians of science recognize that traditional astronomers were skilled empirical observers who developed sophisticated methods for organizing and predicting natural phenomena. Their theoretical frameworks may have been incorrect by modern standards, but their observational data was often quite good, and their mathematical methods were sometimes remarkably elegant. The Ethiopian astronomical tradition also offers insights into the diversity of human approaches to understanding the cosmos. Western history of science has often presented astronomy as a linear progression from Greek antiquity through Islamic scholarship to European Renaissance astronomy, and finally to modern astrophysics. But this narrative overlooks parallel traditions that developed in Ethiopia, India, China, Mesoamerica, and elsewhere. Traditions that asked different questions, developed different methods, and arrived at different, but often equally valid, practical solutions. What endures from Ethiopia's ancient sky-watching traditions? Certainly the calendar itself, still structuring time for millions of people, but also a broader cultural memory that the heavens can be understood through patient observation and careful thought, that knowledge built slowly over generations has lasting value, and that distinctive cultural traditions are worth preserving even in a globalizing world. The monasteries that once served as observatories may no longer train astronomers in the traditional sense, but they remain repositories of texts and traditions that document a remarkable intellectual achievement. For travelers visiting Ethiopia today, traces of this astronomical heritage appear in unexpected places. Churches still align with celestial directions, their orientation reflecting the same attention to solar angles that guided the builders of ancient Axum's monuments. Religious festivals follow the traditional calendar, creating annual rhythms that have repeated for well over a millennium. Elder scholars in remote monasteries still know the old calculation methods and can determine the date of Easter for any year without computers or even written tables, carrying algorithms in their memories that encode centuries of astronomical observation. The story of Ethiopian astronomy is ultimately a story about what humans can achieve through sustained attention, institutional continuity, and cultural commitment to understanding the natural world. Without telescopes, without computers, without even accurate mechanical clocks, Ethiopian astronomers mapped the heavens, understood celestial cycles, created predictive models, and developed a calendar system sophisticated enough to serve a complex agricultural society and a demanding religious tradition. They did this not through sudden breakthroughs or individual genius, but through the slow accumulation of careful observations across generations, each building on the work of predecessors and contributing knowledge for successors. In our modern age of digital calendars that automatically adjust for time zones, leap years, and calendar systems, it's easy to forget that for most of human history, keeping track of time required genuine astronomical knowledge. Someone had to watch the sky, note the patterns, perform the calculations, and maintain the calendar. Ethiopian astronomers did this work for their society, creating tools that served practical needs while also satisfying deeper human desires to understand the cosmos and our place within it. The legacy lives on, not just in the calendar still used today, but in the principle that traditional knowledge, carefully preserved and transmitted, can retain relevance across centuries. The star watchers of ancient Aksum could not have imagined the modern world their distant descendants would inhabit, but they would surely recognize and appreciate that the calendar they helped develop, refined through patient observation of those same stars that still wheel overhead each night, continues to organize time in the Ethiopian highlands. Their work was never finished. Each generation added refinements, corrected errors, and adapted methods to new needs, and in a sense, it continues still. The concept of time is perhaps humanity's most abstract yet essential invention. Unlike physical objects we can touch or manipulate, time exists only as a construct, a framework we impose on the continuous flow of existence to make sense of change, sequence, and duration. Every culture that has ever existed has wrestled with this challenge, developing systems to measure, record, and communicate temporal information. The Ethiopian system, rooted in the ancient Ge'ez language and shaped by centuries of astronomical observation, represents one of the most distinctive and enduring solutions to this universal human challenge. To understand the Ge'ez calendar fully, we must first appreciate that it is not merely a tool for marking dates. It is a comprehensive temporal architecture that integrates multiple cyclical patterns: the solar year, the lunar month, the 7-day week, the 19-year metonic cycle, and various longer cycles that stretch across centuries. These interlocking cycles create a complex but remarkably coherent system for organizing time at every scale, from the hours of a single day to the sweep of centuries and millennia. The foundation of this system is the solar year, which the Ge'ez calendar divides into 13 months. As we've mentioned, 12 of these months contain exactly 30 days each, creating a beautifully regular structure. Each month begins on the same day of the week from year to year in non-leap years, creating predictable patterns that made calendar use intuitive once the basic structure was understood. A person who knew that Mescarim-1 fell on a Wednesday in 1 year could be confident that Tikimtwan would fall on a Friday, 30 days later, or 4 weeks plus 2 days, Hidar-1 on a Sunday, and so forth through the year. This regularity was not merely convenient, it was mathematically elegant. The 30-day month meant that each month contained exactly 4 weeks plus 2 days. Multiply 12 months by 2 extra days, and you get 24 days, or 3 weeks and 3 days. Add the 5 days of Pagum, and the total extra days beyond an even number of weeks equals 29, or 4 weeks plus 1 day. This meant that if year 1 began on a Monday, year 2 would begin on a Tuesday, year 3 on a Wednesday, and so forth, with each regular year advancing the starting day by 1 position in the weekly cycle. Leap years disrupted this simple progression by adding an extra day to Pagum, creating 35 extra days beyond the 48 complete weeks, 336 days in the 12 regular months. 35 days equals exactly 5 weeks, so a leap year advances the starting day of the week by 2 positions instead of 1. This creates a 28-year cycle called the solar cycle, after which the calendar dates return to the same days of the week. Understanding this cycle was crucial for calendar calculation, as it allowed computists to determine the day of the week for any date without having to count forward day by day from some known starting point. But the solar cycle alone was insufficient for the most important calendar calculation required by the Ethiopian Church, determining the date of Easter. As we've discussed, Easter depends on lunar phases as well as solar dates, requiring the integration of the 19-year Metonic cycle with the 28-year solar cycle. These 2 cycles reach the same relative positions simultaneously only once every 532 years, a period known as the Great Paschal Cycle or the Victorian Cycle. After 532 years, the entire pattern of Easter dates repeats, assuming no calendar reforms or adjustments intervene. This 532-year cycle represents the fundamental temporal architecture of the Ethiopian ecclesiastical calendar. Within this grand cycle, every possible combination of golden number, position in the 19-year lunar cycle, and solar cycle position occurs exactly once. This means that a complete table of Easter dates for 532 years could theoretically serve forever, simply repeating once the cycle completes. Medieval Ethiopian manuscripts sometimes contained such extensive tables, though producing them required enormous labor and occupied many pages of expensive vellum. The practical calculation of Easter in any given year required determining several key values. We've mentioned the golden number and the epact, but there were other crucial elements as well. The epact, remember, represents the age of the moon on the first day of the year, and it advances by 11 days each year because 12 lunar months total only 354 days compared to the 365-day solar year. When the epact reaches 30 or more, it's reduced by 30, representing 1 complete lunar month, creating a saltus lunae, or leap of the moon, that keeps the epact within proper bounds. But the epact alone doesn't tell you when Easter occurs. It only tells you the moon's age at the start of the year. To find Easter, you must determine when the first full moon after the spring equinox occurs. The spring equinox in the Ethiopian calendar is fixed at megabit 10, approximately March 21st in the Julian calendar, though the Ethiopian and Julian calendars have now diverged enough that this correspondence is not exact. Using the epact, you calculate how many days after the beginning of the year the first full moon occurs, then determine whether this full moon falls before or after megabit 10. If the full moon falls on or after megabit 10, that full moon is the Paschal full moon, and Easter falls on the following Sunday. If the full moon occurs before megabit 10, you must wait for the next full moon, approximately 29.5 days later, and Easter falls on the Sunday following that second full moon. But finding the following Sunday requires knowing what day of the week the full moon falls on, which requires knowing what day of the week megabit 10 falls on in the year in question, which brings us back to the solar cycle and the calculation of the dominical letter. The dominical letter, a term derived from the Latin Dominicus, meaning of the Lord, and referring to Sunday, is a letter designation A through G, assigned to each day of the year to identify Sundays. In a year where January 1st falls on Sunday, every day with letter A is a Sunday, and the dominical letter for that year is A. If January 1st falls on Monday, then the first Sunday is January 7th, which receives letter A, making A the dominical letter for the year. The system cycles through the 7 letters as it cycles through the 7 days of the week. Leap years complicate this system because adding February 29 disrupts the weekly pattern. In a leap year, the dominical letter changes after February 28. Technically, such years have 2 dominical letters, one for January and February, another for March through December. This means that in leap years, you must track which dominical letter applies to which period when calculating the day of the week for dates later in the year, including the potential Easter dates in late March and April, or their Ethiopian calendar equivalents in late Megabit and Miazia. Ethiopian computists developed various mnemonic devices and calculation shortcuts to manage these complexities. Some used finger-counting methods, assigning each finger joint to different values and moving through standardized counting sequences to arrive at the needed results. Others relied on memorized verse formulas that encoded the calculation algorithms in rhythmic, easily remembered language. Still others used physical calculation aids, counting boards with movable markers, or written tables that could be consulted and cross-referenced to find the needed values. The linguistic dimension of this computational tradition is particularly fascinating. The Ge'ez language, which emerged as a written language in the first centuries of the Common Era and gradually evolved into the liturgical language of the Ethiopian Church, though no longer spoken as a native language by any community, developed specialized vocabulary for temporal and astronomical concepts. The precision of this vocabulary reflects centuries of refinement, as scholars sought exact terms for the phenomena they observed and calculated. For instance, Ge'ez distinguishes between different types of months. The where, meaning month in a general sense, could be modified to specify Werha Sehe, solar month, or Werha Kamar, lunar month. There were specific terms for the phases of the moon, for the position of the sun in the zodiac, for the various types of days, feast days, fast days, ordinary days, and for the elements of calendar calculation. This linguistic precision enabled clear communication of complex temporal concepts and ensured that computational instructions could be transmitted accurately from teacher to student. The written transmission of calendrical knowledge involved not just the recording of calculation methods, but also the explanation of their astronomical and theological rationale. Ethiopian manuscripts often begin calendrical sections with cosmological discussions, explaining the structure of creation, the movements of celestial bodies, and the divine wisdom manifest in the regularities of time. These passages served multiple purposes. They provided context for the calculation methods, they affirmed the theological importance of the work, and they transmitted a worldview in which mathematical order reflected spiritual truth. One particularly important category of texts is the anaphora commentaries, elaborate explanations of the liturgical prayers used in the Ethiopian Orthodox liturgy. These commentaries often include calendrical material because the proper performance of the liturgy depends on knowing the liturgical season, which in turn depends on the calendar. A priest preparing to celebrate the Eucharist needed to know whether the day was a feast or fast, which saints were commemorated, what season of the liturgical year was current, and how many days remained until the next major festival. All of this information came from calendrical calculation. The integration of calendar knowledge into liturgical practice meant that Ethiopian priests received at least basic training in temporal computation as part of their clerical education. Not every priest needed to be an expert computist capable of calculating Easter for arbitrary years, but every priest needed to understand the current liturgical season, consult the calendar correctly, and conduct services appropriate to the day. This widespread basic calendar literacy, distributed across hundreds or thousands of clergy throughout Ethiopia, helped preserve calendrical knowledge even when expert computists were scarce. The monasteries where the most advanced astronomical and calendrical study occurred developed distinct pedagogical traditions and sometimes slight variations in calculation methods. A student trained at Debre Libanos Monastery in Shewa might learn slightly different computational techniques than a student trained at Debre Damo in Tigray, though both would arrive at the same results for important calculations like the date of Easter. These regional variations in method, while never producing significant practical differences, reflected the organic development of knowledge in different communities, each preserving and transmitting their received traditions. The physical manuscripts themselves reveal much about how calendrical knowledge was valued and preserved. Many astronomical and calendrical texts were produced as small, portable volumes that a traveling scholar or priest could carry. These pocket-sized manuscripts, written in tiny but precise script, contained the essential tables and formulas needed for calendar calculation. Their size and portability suggest they were working tools, meant to be consulted regularly rather than merely preserved as reference works. Other calendrical manuscripts were much larger and more elaborate, with illuminated decorations, multiple colors of ink, and careful layout that made tables easy to read and consult. These prestige manuscripts, often produced for important monasteries or wealthy patrons, represented not just practical tools, but also demonstrations of cultural sophistication and religious devotion. The act of producing such a manuscript, which might require months or years of scribal labor, was itself a spiritual practice, a meditation on the divine order reflected in temporal regularities. The preservation of these manuscripts through centuries of political upheaval, warfare, environmental challenges, and simple material decay represents a remarkable feat of cultural continuity. Ethiopian monasteries, often located in remote and defensible locations, perched on mountaintops, hidden in valleys, built in caves, provided relatively safe repositories for texts even during periods of conflict. Monks dedicated to preserving their libraries sometimes went to extraordinary lengths to protect manuscripts, hiding them in sealed caves or carrying them to even more remote locations when threats approached. Yet manuscript preservation was not merely about physical protection. It also required ongoing use and copying. Manuscripts that were consulted regularly, that taught each new generation of scholars, remained alive in a sense, their knowledge actively maintained and transmitted. Manuscripts that were merely stored, never read or copied, risked becoming incomprehensible as the language and notation evolved, or simply deteriorating from neglect. The manuscripts that survived best were those that remained embedded in living traditions of study and practice. This living transmission created an interesting historical dynamic. The manuscripts we have today represent not the oldest or most original sources of Ethiopian astronomical knowledge, but rather the texts that proved most useful and were therefore copied most frequently. Many early texts likely existed but disappeared, their contents either absorbed into later works or simply lost when the last copy deteriorated. What survives is not necessarily what was most historically significant, but what proved most practically valuable across the centuries. The question that emerges from examining this rich tradition of calendrical knowledge is, how did the theoretical and computational aspects of the calendar connect to the lived experience of time for ordinary Ethiopians? How did the elaborate calculations performed by expert computists translate into the daily, weekly, monthly, and annual rhythms of life in Ethiopian communities? To answer this, we must examine not just the technical operation of the calendar system, but its social and cultural embedding, the ways it shaped and was shaped by the people who lived according to its temporal architecture. The calendar, for all its mathematical sophistication and astronomical precision, would have been merely an intellectual curiosity if it had not connected deeply with the lived experience of ordinary people. In Ethiopia, the Ge'ez calendar was never confined to monastery libraries or the studies of learned computists. It structured daily life, organized agricultural work, shaped social interactions, and created the rhythmic framework within which people understood their place in time. This section explores how abstract calendar calculations manifested in concrete social practices and how a society organized its collective life around a distinctive temporal system. The day itself, as the most fundamental unit of time, reveals the calendar's practical embedding. In traditional Ethiopian time reckoning, the day does not begin at midnight, as in modern Western convention, but at sunrise. This means that what Western clocks would call 7 a.m. is 1 o'clock in Ethiopian time, the first hour of the day. Similarly, 1 p.m. is 7 o'clock, 6 p.m., sunset, marks 12 o'clock, and the evening hours count from 1 again. This system, which remains in use in Ethiopia today alongside Western time conventions, reflects a more intuitive understanding of the day as the period of light, with dawn and dusk serving as natural boundaries. This dual time system, with hours counted from sunrise for daytime and from sunset for nighttime, might seem confusing to outsiders, but it aligned perfectly with the rhythms of agricultural life. Farmers did not work by clock hours, but by sunlight. They rose at dawn, worked through the daylight hours, and retired at dusk. The actual clock time of these activities shifted with the seasons, earlier in summer when days were long, later in winter when days were short. But the experiential time remained constant. The first hour of the day always meant the beginning of the work period, regardless of whether that corresponded to 6 a.m. or 7 a.m. in Western reckoning. The week, consisting of 7 days, as in most Christian traditions, carried strong religious significance. Each day of the week was associated with particular biblical events, saints, or theological concepts. Sunday, Ehud commemorated the resurrection of Christ and was the primary day of communal worship. Monday, Segno, was associated with angels. Tuesday, Maksegno, commemorated particular saints. Wednesday, Erob, commemorated the betrayal of Christ. Thursday, Hamas, was named for the covenant. Friday, Abi, commemorated the crucifixion. Saturday, Kidame, was associated with Mary and various saints. This religious overlay on the weekly cycle meant that every week recreated in miniature the fundamental narrative of Christian salvation. Wednesday and Friday, as days commemorating Jesus' betrayal and crucifixion, were regular fast days for observant Christians. No animal products were consumed on these days throughout the year except during a few feast periods when the fast was lifted. This weekly fasting pattern created a regular rhythm of dietary restriction and release that marked the passage of time viscerally through the body's experience of hunger and satiation, restriction, and indulgence. Beyond the weekly cycle, the monthly structure created its own patterns. Each month, as we've noted, contained exactly 30 days, and this regularity made certain date calculations simple. The 10th day of any month, for instance, always fell on the same day of the week as the first day, as did the 20th and 30th. This meant that monthly commemorations and observances were easy to track without elaborate calculation. If you knew that a particular saint's feast fell on the 15th day of a month, and you knew what day of the week that month began, you automatically knew what day of the week the feast would occur. The month names themselves carried seasonal associations that guided agricultural activity and social planning. Mescarum, beginning in early September by the Western calendar, marked the Ethiopian New Year and the end of the heavy rains. This was traditionally a time of celebration, of fresh beginnings, and of the early harvest of some crops. The timing of New Year at the conclusion of the rainy season, when the countryside was green and fresh, when rivers ran full and the landscape bloomed, gave the celebration a natural resonance. It truly did mark the beginning of a new cycle of growth and productivity. Tikkimt, the second month, October-November, continued the harvest season and was associated with agricultural abundance. Markets filled with grain, vegetables, and other produce. Farmers who had worked through the growing season now saw the fruits of their labor. This was also a traditional time for weddings, as families could afford celebrations after successful harvests, and the season's pleasant weather, dry and moderate after the heavy rains but before the coldest winter, weather made travel and gathering easier. Hidar, the third month, November-December, began to bring cooler weather to the highlands. This was the time for threshing grain, storing seed for the next planting, and preparing for the winter months. The name Hidar itself was associated with gathering and storage. Communities organized cooperative work parties for major agricultural tasks, with neighbors helping each other thresh grain, repair storage structures, and complete harvest-related work before the coldest weather arrived. Tarsas, the fourth month, December-January, coincided with winter conditions in the highlands, cold nights, sometimes frost, shorter days. This month included the 40-day Advent fast leading to Jena, Ethiopian Christmas, on Tarsas 29. The timing of Christmas at the depth of winter, though inherited from the Julian calendar tradition rather than developed indigenously, took on local meaning. The celebration of Christ's birth as light entering the world resonated particularly during the darkest, coldest time of year. Tyr, the fifth month, January-February, contained the celebration of Timkat, Epiphany, on Tyr 11, commemorating Jesus' baptism. This festival, one of the most important in the Ethiopian liturgical year, involved elaborate processions, the blessing of water, and communal celebrations. The timing in midwinter made the water ceremonies particularly striking. Participants braved cold weather to engage in ritual ablutions, demonstrating religious devotion through physical endurance. Yekatit, the sixth month, February-March, marked the transition from winter toward the small rains of spring. The name Yekahit is associated with this transitional period. Farmers began preparing fields for planting, repairing plows and tools, selecting seed, and planning the coming agricultural season. This was also traditionally a lean time. The harvest abundance of months past had been largely consumed or stored, and new crops had not yet matured. Careful household management was essential to ensure food supplies lasted until the next harvest. Megabit, the seventh month, March-April, contained the spring equinox around Megabit 10 and the beginning of the Lenten fast, leading to Easter. The small rains, Belg, typically began during this month, allowing planting of certain crops. The coincidence of the beginning of agricultural renewal with the Lenten season, a period of spiritual renewal through fasting and prayer, created a natural parallel between physical and spiritual cycles. Just as the land was being prepared to bring forth new life, believers were spiritually preparing for the celebration of resurrection. Miasia, the eighth month, April-May, typically saw the continuation of the small rains and included the celebration of Easter, Fasika, which could fall anywhere from late Megabit through much of Miasia, depending on the lunar calendar. Easter was the pinnacle of the liturgical year, preceded by the strict fast of Holy Week and followed by 50 days of the Easter season. The dating of Easter, according to both lunar and solar criteria, meant that its position within Miasia varied from year to year, adding an element of moving celebration within the fixed monthly structure. Ginbot, the ninth month, May-June, came at the end of the small rains and was associated with early crop growth. The name Ginbot derives from roots related to growth and productivity. This was a time of agricultural maintenance, weeding, protecting crops from birds and animals, monitoring water sources. The work was less intensive than planting or harvest, but required consistent attention. Social and religious life continued its rhythms, with the post-Easter season gradually transitioning toward ordinary time. Sin, the 10th month, June, July, marked the beginning of the main rainy season, Kiremt in many areas. Heavy rains made travel difficult, and rural communities became more isolated as roads turned to mud and rivers rose. This was paradoxically both a time of agricultural activity, as crops grew rapidly with abundant water, and a time when other activities slowed. Building projects halted, long-distance trading diminished, and communities turned inward, focusing on immediate needs and local relationships. Hamli, the 11th month, July to August, continued the main rainy season. The name Hamli is associated with these heavy rains. Crops were reaching maturity, and farmers anxiously watched the weather, hoping for the rains to continue long enough to ensure good harvests, but not so long as to cause crop damage or delay harvest. This period required patience more than intense labor. Having planted and maintained their fields, farmers now waited for nature to complete the growth cycle. Nehes, the 12th month, August-September, saw the waning of the main rains and the beginning of harvest preparations for some crops. The name Nehazi relates to copper or bronze, possibly reflecting traditional metalworking activities that could resume as the rains decreased and traveling smiths could move between communities. This month also began the build-up toward the New Year celebration that would come in early Meskerem, creating a sense of the year approaching its culmination and renewal. Pagum, the 13th month, consisting of only 5 or 6 days, fell outside the regular monthly cycle and was considered a liminal period, a time between times. In many Ethiopian communities, these days were treated as particularly auspicious or spiritually significant. Some traditions held that the boundaries between the visible and invisible worlds became thinner during Pagum. Others saw it as a time for settling accounts, resolving disputes, and preparing spiritually for the new year. The brevity of Pagum gave it an intensity, a concentrated period of transition before the cycle began anew. This monthly cycle, repeating year after year, century after century, created a stable framework within which individual lives and family histories unfolded. People marked their ages not just in years, but in relation to the seasonal cycle. Someone might be described as having lived through 40 planting seasons or 30 Christmas celebrations. Major life events were remembered by their position in the calendar. She was born in Hidar during the year when the harvest failed, or he died in Miazia just after Easter when the Belg rains came late. The commemoration of saints and religious festivals added another layer of temporal texture. The Ethiopian Orthodox Church maintains an extensive synaxarion, a calendar of saints, with multiple saints commemorated on virtually every day of the year. Each saint's day brought particular prayers, readings, and sometimes special observances. Families often had particular devotion to saints whose feast days coincided with family events, or who were associated with family names. This personal connection to the liturgical calendar meant that the abstract flow of days was populated with meaningful anniversaries and observances. The larger cycles, the 19-year Metonic cycle, the 28-year solar cycle, the 532-year Great Paschal cycle, were less immediately visible in daily life, but still structured long-term temporal awareness. Elderly people might note that the calendar had returned to a particular pattern they remembered from their youth, recognizing the completion of a 28-year cycle. Scholars and church officials tracked these longer cycles for calculation purposes, maintaining an awareness of time that extended far beyond individual lifespans. This multi-layered temporal awareness, from the hours of the day to the centuries-long cycles, created a rich sense of living within nested rhythms, each with its own significance. Time was not uniform or abstract, but textured and meaningful. Each moment existed within multiple cycles simultaneously, within a day, within a week, within a month, within the liturgical year, within longer astronomical cycles. Understanding where you were in all these cycles simultaneously, knowing, for instance, that it was the third hour of Friday in the week before Timcat during a leap year when Easter would be late, provided a comprehensive temporal orientation. The social coordination required by this calendar system fostered particular forms of community and authority. Someone had to maintain the calendar, announce feast days, determine when fasts began and ended, and calculate the date of movable festivals. In most communities, this role fell to clergy, local priests who had received sufficient education to consult calendrical tables and perform basic calculations. These priests served as temporal authorities, their knowledge giving them social status and practical influence. For more complex calendar questions, determining the date of Easter for future years, resolving uncertainties about when particular observances fell, or clarifying ambiguities in calendar calculation, communities might consult scholars at nearby monasteries or seek written calendar materials from major religious centers. This created networks of expertise and knowledge transmission that connected local communities to broader institutional structures. A village priest might maintain the day-to-day calendar, but defer to a monastery scholar for specialized calculations. The calendar also structured economic life in ways that went beyond agricultural timing. Market days occurred on fixed schedules, often weekly, bringing together rural producers and urban traders. These market cycles, synchronized with the calendar, created predictable opportunities for exchange. Traders knew when and where markets would occur, allowing them to plan travel and coordinate activities across regions. Tax collection, tribute payment, and other economic obligations were similarly tied to calendar dates, creating temporal landmarks in the economic year. Legal and administrative systems incorporated the calendar as well. Contracts specified performance dates using the Ethiopian calendar. Land transactions were dated and recorded according to the regnal year of the emperor and the month and day in the Ethiopian system. Court proceedings tracked dates of offenses, testimonies, and judgments using the traditional calendar. This meant that legal literacy required calendar literacy, understanding dates, calculating intervals, and determining when obligations were due. The calendar even shaped warfare and conflict. Military campaigns typically followed seasonal patterns dictated by weather and agricultural cycles. Armies moved during dry seasons when roads were passable and food supplies were available. The main rainy season, when military movement was difficult, often brought temporary cessations of conflict. Peace negotiations and treaties were dated according to the Ethiopian calendar, and truce periods were often defined by reference to religious festivals until 30 days after Easter, or until the Feast of Timkat. This deep integration of the calendar into every aspect of social life meant that challenges to the calendar system were not merely technical or religious issues, but struck at the heart of social organization. When European colonial powers and modernizing influences brought pressure to adopt the Gregorian calendar, the resistance was not simply conservative adherence to tradition, but defense of an entire way of organizing collective life. To change the calendar was to disrupt agricultural coordination, alter religious observances, complicate legal documentation, and require massive social readjustment. Yet the calendar's resilience through these challenges demonstrates something important about cultural systems that successfully integrate technical knowledge with social practice. The Ethiopian calendar endured not because it was imposed by authority or maintained by force, but because it served genuine social needs and carried cultural meaning. It worked. It organized agricultural life effectively. It coordinated religious observances successfully. It structured social interaction coherently. Its astronomical basis gave it objective validity, but its social embedding gave it practical value and emotional resonance. This raises a profound question about the relationship between knowledge systems and the societies that develop and maintain them. How do technical innovations, like calendar systems, become naturalized into culture so thoroughly that they seem inevitable rather than constructed? How do human creations come to structure human experience so completely that they shape how people understand reality itself? And what happens when such deeply embedded systems encounter alternative frameworks that claim equal or superior validity? These questions become particularly pressing when we consider how the Ethiopian calendar system adapted or resisted adaptation in response to modernization, globalization, and the dominant international temporal standards of the 20th and 21st centuries. The 20th century brought unprecedented challenges to traditional Ethiopian timekeeping. The forces of modernization, colonial influence, technological change, and globalization all exerted pressure on the distinctive temporal systems that had organized Ethiopian life for well over a millennium. Yet remarkably, the Ethiopian calendar not only survived these pressures, but maintained its position as the official calendar of the Ethiopian state and the primary temporal framework for millions of people. Understanding how this occurred and what it reveals about the resilience of cultural knowledge systems provides insight into the broader dynamics of tradition and change in the modern world. The first major challenge came with increased European contact in the late 19th and early 20th centuries. European powers, having adopted the Gregorian calendar in the 16th through 18th centuries, regarded it as the universal standard for timekeeping. When European merchants, missionaries, diplomats, and eventually colonizers arrived in Ethiopia, they brought with them not just different calendar dates, but fundamentally different assumptions about time, scheduling, and temporal organization. The resulting friction was not merely practical inconvenience, but represented a collision between different ways of structuring reality. For European visitors, the Ethiopian calendar seemed backward, inefficient, and unnecessarily complicated. Why maintain a 13-month calendar when the modern world used 12? Why calculate dates differently from international standards? Why persist with a calendar that placed the year in a different century from the Gregorian system? These questions reflected a broader European assumption that Western systems represented progress and that traditional non-Western systems should be abandoned in favor of modern, rational, universal standards. Ethiopian intellectuals and officials responded to these challenges in various ways. Some, particularly those educated in European institutions or heavily influenced by European thought, advocated for calendar reform and adoption of the Gregorian system. They argued that Ethiopia's integration into the modern world economy and international diplomacy required conformity to international temporal standards. Using a different calendar, they suggested, isolated Ethiopia and created unnecessary barriers to communication and coordination with other nations. Others, however, defended the traditional calendar vigorously. They pointed out that the Ethiopian calendar functioned perfectly well for its purposes, that it was deeply integrated into religious and agricultural life, and that changing it would require massive social disruption with little practical benefit. They noted that the Gregorian calendar was not inherently superior, but simply reflected Western Christian traditions, and that Ethiopia's calendar reflected equally valid Eastern Christian traditions with deeper historical roots in some respects. Why should Ethiopia abandon its own traditions to conform to European preferences? This debate intensified during the Italian occupation from 1936 to 1941. The fascist Italian government, seeking to impose European administrative systems on occupied Ethiopia, attempted to mandate use of the Gregorian calendar for official purposes. Italian occupiers issued documents dated according to the fascist calendar, which itself was a modification of the Gregorian calendar, counting years from Mussolini's 1922 march on Rome, and demanded that Ethiopian institutions adopt European temporal systems. This colonial imposition had an unintended effect. Rather than making the Gregorian calendar seem modern and progressive, the Italian occupation associated it with foreign domination and cultural suppression. The Ethiopian calendar became, in some sense, a symbol of resistance. Maintaining traditional timekeeping was a way of asserting Ethiopian identity and rejecting colonial cultural hegemony. When Ethiopia regained independence in 1941, one of the acts of cultural restoration was the reaffirmation of the traditional calendar system. Emperor Haile Selassie, who ruled Ethiopia through most of the mid-20th century, navigated between these competing pressures with characteristic pragmatism. He maintained the Ethiopian calendar as the official system for domestic purposes, while ensuring that Ethiopia could function in international diplomacy using Gregorian dates. Government documents were often dated with both systems. Diplomatic communications used Gregorian dates when addressed to foreign governments, and Ethiopian officials learned to translate between the two systems fluently. This bilingual temporal approach, using Ethiopian dates internally and Gregorian dates for international purposes, became the compromise solution that allowed Ethiopia to maintain its traditional system while participating in global institutions. Ethiopian newspapers began printing both dates. Airlines and other international businesses operating in Ethiopia used dual dating systems. Schools taught both calendars, ensuring that students could navigate both temporal frameworks. The technological changes of the 20th century created new challenges for the traditional calendar. Mechanical clocks and watches, produced primarily in Europe and America, used 12-hour dials suited to the Western day counting system. These devices were not naturally compatible with Ethiopian time reckoning, which counts hours from sunrise and sunset rather than from midnight. Ethiopians adapted by learning dual time systems, using Ethiopian time for local interactions and Western time for situations involving international coordination. Radio broadcasting, which began in Ethiopia in the 1930s and expanded dramatically in the latter half of the 20th century, required establishing standard time signals and programming schedules. Ethiopian radio broadcasters developed the practice of announcing programs in both time systems. The news will air at 6 o'clock Ethiopian time, 12 o'clock international time. This dual announcement became so routine that Ethiopians learned to translate between systems almost unconsciously. The introduction of computers and digital systems in the late 20th century created particularly complex challenges. Computer operating systems and software were designed primarily for Western markets and built around the Gregorian calendar. Making these systems work with Ethiopian dates required either complex conversions or specialized software. Ethiopian programmers developed conversion algorithms and created custom applications that could handle Ethiopian dates. But the process was cumbersome and prone to errors. Database systems, spreadsheets, and scheduling software all assumed Gregorian dates as the default. Ethiopian users had to either work entirely in Gregorian dates, defeating the purpose of maintaining the traditional calendar, or manually convert between systems constantly. This created practical difficulties in business, government administration, education, and virtually every sector touched by computerization. The problem was not insurmountable, but it represented a significant practical burden that advocates of calendar modernization pointed to as evidence that Ethiopia should finally abandon its traditional system. Yet rather than capitulating to these pressures, Ethiopian software developers and entrepreneurs created solutions. They developed Ethiopian calendar plugins for popular operating systems, created Ethiopian date calculators and conversion tools, built scheduling applications that natively supported Ethiopian dates, and even created custom operating systems designed around the Ethiopian temporal framework. This indigenous technological innovation demonstrated that traditional systems could be maintained even in the digital age if sufficient creativity and effort were invested. The religious dimension remained central to the calendar's persistence. The Ethiopian Orthodox Church, as the custodian of calendrical knowledge and the institution most invested in maintaining traditional timekeeping, consistently resisted calendar reform. Church leaders argued that the calendar was not merely a practical tool, but a sacred trust, that the calculation of Easter and other feasts according to traditional methods was a religious obligation, and that abandoning the traditional calendar would sever Ethiopia's connection to its Christian heritage. The theological arguments went deeper than mere conservatism. Ethiopian Orthodox theology emphasizes continuity with ancient Christian traditions, particularly the traditions of the early church fathers and the councils of the first centuries of Christianity. The Ethiopian calendar's basis in the Alexandrian computational tradition, the methods used by the early church in Egypt and transmitted to Ethiopia in the first centuries of Ethiopian Christianity, represented a direct link to this ancient tradition. To abandon the traditional calendar would be to break this historical continuity and implicitly suggest that modern convenience mattered more than theological fidelity. Monasteries continued to serve as centers of calendrical knowledge, even as the broader society modernized. Young monks still learned the traditional computational methods, still studied the Bahir Hasab texts, still practiced calculating Easter dates using the ancient algorithms. This preservation of traditional knowledge occurred even as many monks also learned modern mathematics, used computers, and engaged with contemporary technology. The traditional and modern coexisted, neither completely displacing the other. This monastic preservation proved crucial during the communist Derg period from 1974 to 1991. The Derg government, ideologically opposed to religion and seeking to modernize Ethiopia according to Marxist principles, suppressed many religious institutions and practices. Churches and monasteries were closed or repurposed, religious education was restricted, and traditional cultural practices were discouraged in favor of secular, modernist alternatives. The calendar, however, proved too deeply embedded in daily life to be effectively suppressed. Even under the Derg, farmers continued to plant according to traditional timing, families continued to observe religious fasts and feasts, and communities continued to track time according to the familiar monthly cycle. The government might use Gregorian dates for official documents, but ordinary people conducting their daily affairs used the Ethiopian calendar. This grassroots continuity meant that when the Derg fell in 1991 and restrictions on religious practice were lifted, the traditional calendar system was still intact, still understood, still functioning. The post-1991 period brought new dynamics. The Ethiopian government officially reaffirmed the Ethiopian calendar as the country's civil calendar, while also recognizing the practical necessity of the Gregorian calendar for international interactions. This dual calendar policy was formalized in various ways. Official government calendars printed both systems. School curricula included instruction in both calendars, and public institutions developed standardized approaches to dual dating documents. Globalization accelerated dramatically in the late 20th and early 21st centuries, bringing Ethiopia into increasingly dense networks of international communication, commerce, and cultural exchange. The internet, mobile phones, international travel, and global media all operated primarily on Gregorian time. Young Ethiopians growing up in this globalized context often learned the Gregorian calendar first, or simultaneously with the Ethiopian calendar, and many found the Gregorian system more convenient for international interactions. Yet paradoxically, globalization also created renewed interest in cultural distinctiveness. As global culture seemed to homogenize, there was a counter-movement to celebrate and preserve unique local traditions. The Ethiopian calendar, as one of the most visible markers of Ethiopian distinctiveness, became a source of cultural pride. Rather than being seen as backward or inconvenient, the calendar was increasingly framed as a unique cultural treasure that set Ethiopia apart from the global mainstream in positive ways. This reframing was particularly evident in diaspora communities. Ethiopians living in Europe, North America, and other parts of the world often maintained the Ethiopian calendar as a way of preserving cultural identity in foreign environments. Ethiopian New Year celebrations in diaspora communities became major cultural events, opportunities to gather, affirm identity, and transmit traditions to children growing up in different cultural contexts. The calendar became not just a practical tool, but a cultural symbol, a marker of Ethiopian identity that could be maintained even when separated from the Ethiopian landscape, climate, and immediate social context. Tourism also contributed to the calendar's valorization. International tourists visiting Ethiopia were often fascinated by the country where it's 7 years earlier, or the land of 13 months of sunshine, a slogan that plays on the 13-month calendar structure. Tour guides explained the calendar system. Hotels provided calendars showing both date systems, and the unique temporal framework became part of Ethiopia's tourism brand. This external interest reinforced domestic pride in the distinctive system. Academic scholarship on the history of science and the history of timekeeping also contributed to new appreciation for traditional calendar systems. Historians of astronomy and anthropologists studying temporal systems began to recognize that Ethiopian calendar traditions represented sophisticated astronomical knowledge and mathematical computation. Rather than viewing these traditions as primitive approximations of modern scientific understanding, scholars came to see them as alternative knowledge systems with their own validity, logic, and practical effectiveness. This scholarly revaluation had practical effects. Ethiopian universities developed programs studying traditional astronomical and calendrical knowledge. Manuscripts in monastery libraries received new attention from researchers. Elderly scholars who still practiced traditional computational methods were interviewed and recorded, their knowledge documented before it could be lost. Government and NGO-funded projects worked to digitize ancient texts, create databases of calendrical knowledge, and preserve this heritage for future generations. The question of calendar reform never entirely disappeared, but it shifted from should Ethiopia abandon its traditional calendar to how can Ethiopia maintain its traditional calendar while functioning effectively in a globalized world. This reframing acknowledged both the practical challenges and the cultural value of the distinctive system, seeking technological and institutional solutions rather than cultural capitulation. Modern Ethiopian calendar applications for smartphones represent a fascinating synthesis of ancient and contemporary. These apps calculate Ethiopian dates using algorithms ultimately derived from the same mathematical principles described in medieval Bahir Hassab texts, but they run on cutting-edge technology. Users can see both Ethiopian and Gregorian dates simultaneously, receive notifications for religious feasts and fasts according to the Ethiopian liturgical calendar, and even calculate Easter dates for future years. All the functionality of traditional calendrical computation, but accessible instantaneously through modern interfaces. This technological adaptation demonstrates that traditional knowledge systems can persist not by remaining frozen in historical forms, but by adapting to new contexts while maintaining core principles. The Ethiopian calendar of the 21st century differs in many practical respects from the calendar of the 15th or 10th centuries. It's accessed through different media, taught in different educational contexts, used alongside alternative systems, but the fundamental mathematical and astronomical principles remain the same. The human cost of maintaining this system should not be overlooked. Ethiopian students must learn 2 calendar systems where students in most countries learn only 1. Ethiopian programmers must create custom solutions where others can use off-the-shelf software. Ethiopian businesses dealing internationally must constantly translate between temporal frameworks. Every Ethiopian who interacts with the global economy or international institutions bears some burden of calendar difference. Yet the persistence of the system demonstrates that people and societies will sometimes choose to bear such costs when the alternative is surrendering elements of identity and tradition they value deeply. The Ethiopian calendar survives not because it's more convenient or more accurate than alternatives, but because it connects contemporary Ethiopians to their history, embeds them in religious and agricultural cycles that give life meaning and structure, and marks them as distinct in a homogenizing world. The keepers of cosmic time today are not only the monks in monastery scriptoria copying ancient manuscripts, though they continue their important work. They are also the programmers writing calendar conversion software, the teachers explaining the system to new generations, the parents teaching children to count time in the traditional way, the government officials maintaining dual dating systems, and the millions of ordinary Ethiopians who continue to organize their lives according to the 13-month year, the hours counted from sunrise, and the liturgical seasons calculated by ancient astronomical methods. Looking forward, the future of the Ethiopian calendar is not assured, but seems reasonably secure. As long as the Ethiopian Orthodox Church maintains its influence, and with roughly half of Ethiopia's population affiliated with the Church, its influence remains substantial. The religious imperative for the traditional calendar will persist. As long as Ethiopian agriculture follows seasonal patterns tied to the solar year, the calendar's practical utility will remain. As long as Ethiopian cultural identity values distinctiveness and historical continuity, the calendar will serve as a powerful symbol worth preserving. The broader lesson that Ethiopian calendar persistence offers is that knowledge systems embedded in social practice and cultural meaning can endure through enormous pressures for change. They endure not through isolation from alternatives, but through adaptation, not through rejecting modernity, but through finding ways to be modern while remaining distinctive, not through force, but through the voluntary choices of millions of people who find value and meaning in traditional frameworks. The star watchers of ancient Aksum, who first systematized observations of the heavens, could not have imagined the 21st century world in which their intellectual descendants would live. They could not have foreseen computers, smartphones, global communications networks, or the myriad ways that time would be measured, disseminated, and coordinated in the modern era. But they established a framework robust enough, meaningful enough, and practical enough to survive across millennia, adapting to each new context while maintaining continuity with its origins. Perhaps this is the ultimate achievement of the Ethiopian astronomical and calendrical tradition. Not that it produced the most accurate measurements or the most sophisticated mathematical models, but that it created a system so deeply woven into the fabric of a culture that it could weather enormous changes while retaining its essential character. The calendar lives because the culture that created it continues to value the temporal architecture it provides, finding in the regular succession of months, the cycling of liturgical seasons, and the calculated precision of feast day timing, a framework that makes time itself meaningful. In a world increasingly dominated by universal standards and homogenizing systems, the persistence of distinctive cultural frameworks like the Ethiopian calendar reminds us that human diversity includes temporal diversity, different ways of organizing, understanding, and experiencing that most fundamental dimension of existence, time itself. The Ethiopian calendar stands as testament to the proposition that there is more than one valid way to structure time, more than one legitimate calendrical tradition, and that the value of a system lies not just in its technical precision, but in the human meanings it carries and the cultural continuity it enables.